So let's talk about address pointers in embedded C or C needed for microcontrollers. Now, the way C is written on microcontrollers, though similar in many respects with the C that you write for your uh, on your workstation, is still a lot different. One of the major distinguishing factors of C written for embedded systems and on microcontrollers is how address pointers are handled. Because in embedded C, pointers to actual memory addresses is the foundation of almost all programs. So, and embedded C interacts more closely with hardware than coding on C on OSs like Unix, Mac OS, or Windows or Linux. Even though embedded RTOSs exist, still memory access is an integral part of embedded firmware. So, as far as embedded firmware is concerned, you have to allow the code to access the hardware. And if you have been coding on, say, uh, desktop operating systems, you would still be using pointers, but those pointers are going to will not be pointing to any hard coded memory location. But that is the case here. So here, in the case of a microcontroller, we will need to access a lot of memory locations which are there. So you will have to assign hard coded memory addresses to pointers. It is not going to be as if you declare a variable and then you assign the address of the variable to a pointer variable like you do generally, which also is the case, which also is done in the case of embedded C. But manipulating memory, manipulating your peripherals and other control registers is a major part of embedded systems. And there is little to no level of abstraction between the hardware and the software firmware that you write. So memory addressing is mainly needed to have a tighter control over different regions of the controller memory, one of them being access to the peripheral and control registers. So those of you who have been working on 8 and 16-bit architecture will definitely know how the memory is accessed. But in the case of 32-bit controllers also, it is accessed pretty much in the same way through address pointers. Now, memory addressing is mainly needed to have a tighter control, as we discussed. There are various driver libraries provided by chip vendors which try to offset this problem by providing APIs to access the hardware via some abstraction layer. There would be APIs that say your board support package or your your CMSIS library is going to provide some API whereby if you just say write into a location in the flash, or write into this particular register with the register name, in the backend actually it is going to do a memory write to some location in the flash which is intended. Since this is a bare metal course, we are not going to again take the help of any library, vendor provided library. We are going to write our own memory access routines. However, we are going to reuse the CMSIS header file for memory map. So CMSIS memory map header file is going to be used by us, and that memory map file again has been changed to an extent so that it is made simpler and more understandable. And for memory mapping, I have actually brought in more information into that file. So generally for CMSIS, you will need multiple files to do your memory map. But what I have actually consolidated your entire memory map onto one CMSIS file for your convenience. So we'll see all that. Okay, and the memory addresses are mostly defined through macros, which we generally define in header files. So these are macros; they are just hash defined some memory location, and we declare some pointers, and we define them by equating them to some memory location, which is generally a value. A pointer to a memory location can be defined by typecasting a value of say 816 or 32-bit memory with as per the architecture as a volatile unsigned pointer of type int shorter cap. But well, yes, mostly it is volatile, but it need not be volatile all the time. But yes, volatile because uh, so that the compiler can be prevented from making any optimizations, and whenever we are reading that particular memory location, it is indeed accessed. So we will look at two methods for manipulating memory in microcontrollers, of which we will be using the second method. But we will go through both the methods and we'll see how they are used, because that's going to help you, because different vendors will write their memory access code in different ways, though both of them or all of them do the same thing under the hood, but the styles are different. So the first method is so all of them are done through macros, but the first method is like this. It goes hash define and a variable and a value. So this is a macro, and this is your this is the preprocessor directive, and this is your variable, and this is the value that the variable has to be replaced with. Now if we come here, that is these hash define statements. Now this may look a bit more complicated if you have not been exposed to such macros. So let us do it like this. First of all, let's assume that I have to write code to access this memory location. So my first order of task is that I have to access the value in this memory location 0xe000e010. So whenever we have to access value in this memory location, we know that we have to use pointers. So we have to associate this particular memory location with a pointer, or to me, as of now, this is not a memory location, this is just a value. Okay, E000E010 is a value. So how do I associate this value with a pointer variable? So what I can do is, I'll come to this later. So let's first understand this. So what we'll do is, we'll do say volatile unsigned int star equal to typecast this value, volatile unsigned int star, and then put the value here, that is say 0xe000e010. So volatile unsigned int star, some value, of course. So say this is volatile unsigned int, so value now holds the value of this 0xe000e010. It holds the value, and the compiler knows, because of declaring this as a volatile unsigned int, that this is not any value, but this is a pointer value. So the way the compiler deals with this value is different. Though this is just a value, this is just a number, but the compiler, when you declare it as say volatile unsigned int, when you do a star, So as you know, um, as you know, in C pointers, this value, though it's just a value, but C treats this value as a pointer. So it gives it some special attributes, and you cannot treat it like any ordinary variable. So C knows that this is not just an ordinary value. It is pointing to some memory location, and the whole purpose of declaring this is that to tell the compiler that I'm going to use this value as a memory location address. So now if you have to get the value out of this address location, all you need to do is, as you know, dereference the pointer and you get the value out of this memory location. So E000, E010, if you have memory locations, this probably, say, will have some value. Say it has a value of 100. So star value will be 100. So this is standard pointers in C. The only difference that you will observe here is that this is a number. So far, if you have just worked on, or if you have worked on standard C, we would not have dealt with a number as an address location, because that is the job of the driver layer of the operating system. So if you are working on Linux or Windows, you will have a very strong abstraction between actually the hardware addresses and your user space code. So you can only maybe do read write into the handle, the device handle, or you can do IOCTL commands in Linux and so on and so forth. So that's how devices are accessed in the case of your operating systems. But in this case, the access is direct. You access the memory location directly. That is, this is your hardware and your code is running just on top of the hardware, and you are accessing the hardware memory locations directly by assigning straight away numbers to variables, which is also possible in the case of the C program that you do on your desktop. But just try to assign a number, because you first of all, you would not know the address map of the devices. And even if you knew the devices and you try to put an address map that way, you might end up getting problems. That's not how it's done. And since it's all on virtual memory, that is, I'm talking about conventional C, things are more complicated. In this case, you directly access the memory. So this is how you. So here also, like in conventional C, we can actually declare a pointer, and we can define we can assign the address of a variable, say ampersand and some variable, and we'll see that we will see some code doing this. So we can do all that assignment here, but this is the most basic C pointer manipulation, and whatever we discussed here is a short form of doing the same here. When we declare a macro, or when we define a macro, basically what happens is this macro, in a way. So suppose now you have to access another location, memory location, so E018, say. Now, how many times are you supposed to, how many variables do you want to declare like this in your main? It becomes very tiring, because say you have hundreds of registers and which you need to access, and you keep declaring such things in your C code, and so it becomes out of hand very soon. So what we need to do in this case is take the help of these macros. So what these macros do is, so I hope you followed this part. Now what these macros do is, suppose you have So let's take this one. So whatever we had written, this macro does exactly the same, but the values are varied. For example, if you place a value, so say if we take this one, so instead of E000 E010, if we place another value, when the compiler replaces this in the program, it actually replaces this X with that particular value. So what I mean to say is, so you will have different defines here. So SysTick base, and then as you see, has hash defined control and has hash defined other values. So if the hash defined control was say in 0x0004, suppose, okay, so this is just another variable and a value assigned to it through macros. So when you add these two values, you will get E000 E014, correct? So SysTick base plus control is E000 E014, and then you could have other values also here. Okay, for SysTick you could have other register values, and generally you will see in the data sheets also a base will be a base address will be mentioned, and all the registers will be mentioned as offsets to this particular base address. So it will be at an offset of 0x4. There could be byte addressable registers, there could be word addressable registers, so on and so forth. So we'll have a series of defines which will be it could be 000 say C, or 000 0010, and so on. Okay, so these are offsets. So what it essentially means is, if you have a memory location here with the increasing memory this way, if this is E000 E010, there are consecutive memory locations which are your different control registers going this way, increasing memory. And if you want to access say the next memory location, or the next, what you essentially need to do is to add that value. So add the value to the base address, say add 4 to the base address, and then put it in this particular macro, and then access that particular memory location. That's what this says, and that's what you saw there. So how do we do that? So for example, if you broke this particular macro down, it exactly breaks down to whatever we saw when we declared the variable. So ADDR, so if you want to access a 4-byte space, that is 4-byte width value, that is a word, then it is volatile unsigned int. If it is ADDRH, that is if you want to access 2 bytes, it is volatile unsigned short, and ADDRB is volatile unsigned char, that is it accesses 1 byte from that particular memory location. Okay, so suppose we have to access a word from the memory location, say from control, which is say 0004. Okay, so this is from where we have to access it, or we have to write something here. So this is how we do it. So we say we declare an integer. So say it is, because we are getting the value out of it, and that value is an integer. So we are accessing that particular. So we can say integer control register equal to, just do ADDRW. This is anything. This you can give it as anything. Okay, ADDRW, and here you do say these variables can be anything. I've just written it here, but like this, but it can be SysTick underscore base, and then you do plus CTRL. Okay, that's all. When you do that, you'll see that this variable will be filled with the value of whatever is in that memory location. If you want to write into the memory location, you interchange the places. So ADDRW SysTick base equal to control register. Okay, so the control register value is going to come in here, and this is because we are also dereferencing the value. So like we saw, star, the pointer variable is the value dereferenced. So when we do ADDR this, so ADDR this actually breaks down to, so when we do ADDR systic base plus control, so this is how the compiler breaks it up. So it is systic base plus control. Okay, this is the address value, and in front it adds star volatile unsigned int star. So it typecasts this value and then puts a star in front of it. So that breaks down to star volatile. So if I do ADDRW systic base plus control, assuming that they have macros for these two, that is, you have hash defines for these two, it breaks down to this star volatile unsigned int star. Okay, and the summation of these two values, so it becomes 0x E000 E014. Okay, and this value is manipulated. So all of this is actually, this is a shortcut for writing so much. So if you already declare it in the macro, all you need to do is to just say ADDR and systic base plus CTRL, and you get the value out like this. Okay, so I hope you understood this. If you do not, then please leave your questions and I will try to help you out. So instead of typing this or writing this every time, so this is basically how you dereference and access that particular memory location. So this is the key, but you want to shorten it. Every time when you are write code, you don't write this. It's difficult for understanding, it's difficult for keeping track of what memory locations are being accessed. So this is the method of doing it. So this is method 1. So we will look at some code for method 1, and of course when you do volatile unsigned short star, it will go to that particular memory location E000 E014 or any memory location, whatever you have given, and it will access only 2 bytes from there. So it will access E000 E014 and E000 E015. That's all. So 14 and 15 is going to be accessed. Okay, from wherever it is. Okay, so from wherever it is. If it is a byte, it will only access this one, E000 E014. It is not, and if it's of course, if it's a word, it is going to access all 4 bytes here, 14, 15, 16, 17, and so you have to you have to access that value using a word actually. So it could be uint unsigned int 32 or so on. So I hope you understand this part. So this is the most important aspect of embedded systems C programming. That is how you access the real hardware. We'll have a look at some code after this, and that will make it more clear to you.